Welcome to G Fun Facts Online. Today we are diving deep into the invisible architecture of the cosmos. We are going to talk about a concept that transforms our understanding of the universe from a static, frozen picture into a violent, thermodynamic engine. We are talking about the heat death of dark matter, a process known technically as gravothermal collapse. For decades, the standard story of cosmology has been relatively simple, at least regarding the dark sector. We have the cold dark matter model, or CDM. In this view, dark matter consists of these heavy, ghostly particles that move slowly and interact with absolutely nothing, not even themselves, except through gravity. They are inert. They formed the gravitational wells that allowed ordinary matter to fall in and create galaxies. And once those halos formed, they were supposed to be these frozen, collisionless containers. They didn't change much, they just sat there. But recent breakthroughs, culminating in high-resolution simulations and observations from late 2025 and 2026, have shattered that static image. We now have evidence that dark matter is dynamic, it is collisional, and most importantly, it is subject to the laws of thermodynamics in a way that is both beautiful and destructive. To understand why this matters, we have to look at the problems with the old cold dark matter model. CDM was the great architect. It predicted the cosmic web and the large-scale structure of the universe perfectly. But when we zoomed in, things started to break down. This was known as the small-scale crisis. Simulations of cold, ghost-like dark matter predicted that the centers of galaxies should be incredibly dense. Because the particles don't bounce off each other, they sink right to the bottom of the gravitational well, creating a sharp spike in density called a cusp. Nature, however, disagreed. When astronomers looked at nearby dwarf galaxies, they didn't see these sharp cusps. They saw cores. The central regions of these galaxies had a constant, flat density, like a fluffy cloud rather than a dense spike. CDM could not explain this. It was too rigid. This is where self-interacting dark matter, or SIDM, enters the picture. The idea is deceptively simple. What if dark matter particles could collide? What if, occasionally, they bounced off one another? If they have a non-zero cross-section for scattering, the physics changes completely. In the dense center of a halo, these particles start hitting each other. They transfer energy. Just like heat conduction in a gas, the hot, fast-moving particles transfer energy to the cooler ones. This acts as a homogenizer. It puffs up that central density spike, turning it into a flat, thermalized core. For a long time, this was the main selling point of SIDM. It solved the core-cusp problem naturally. It made the halos fluffy, matching what we saw in dwarf galaxies. But that is just the beginning of the story. Thermodynamics is a cruel mistress, especially when gravity is involved. And this brings us to the most counterintuitive concept in astrophysics, the thermodynamics of self-gravitating systems. In a normal gas, like the air in a room, if you remove energy or cool it down, the temperature drops. The molecules slow down. But gravity behaves differently. In a system held together by gravity, like a star or a dark matter halo, the specific heat is negative. That sounds impossible, so let's break it down. If you remove energy from a dark matter core, the core loses support. It can't fight gravity as well, so it contracts. It shrinks. But as it shrinks, the particles fall deeper into the gravitational well. They convert that potential energy into kinetic energy. They speed up. So the result of losing energy is that the system gets hotter. It contracts and speeds up. This sets the stage for a runaway feedback loop called gravothermal collapse. Imagine a dark matter halo. The core is hot, meaning the particles are moving fast. The outer halo is cooler. Heat naturally flows from the hot core to the cool outskirts. The core loses energy. Because of that negative heat capacity we just talked about, losing energy makes the core contract and get even hotter. Now that it is hotter, the temperature difference between the core and the outskirts is even bigger, so heat flows out even faster. This causes more contraction, more heating, and even faster heat loss. It is a catastrophic cycle. The core of the dark matter halo begins to collapse in on itself. The density rises exponentially. The core radius shrinks from thousands of light years across to just a few light years, and then down to sub-parsec scales. The halo is essentially undergoing a heat death, but instead of fading into cold oblivion, it is burning up in a fever of density and speed. We can now map the life of a dark matter halo into three distinct phases. First, there is the core expansion phase. This is the cure for the cusp problem. The interactions vaporize the dense center and create that nice, fluffy core we see in dwarf galaxies. This phase lasts for billions of years. Then comes phase 2, the turnaround. The core effectively becomes a thermal engine. It conducts heat to the vast reservoir of the outer halo. The central density stops dropping and hits a minimum. Finally, phase 3, the gravothermal catastrophe. The collapse accelerates. The dark matter behaves like a fluid. the central density spikes by orders of magnitude. The core collapses until it hits a singular point. Theoretical models suggest that unless some quantum pressure stops it, this core collapses directly into a black hole. This mechanism solves one of the biggest headaches in modern astrophysics, the origin of supermassive black holes. We see giant black holes, billions of times the mass of the Sun, existing when the universe was only 800 million years old. Standard theory cannot explain this. You simply cannot grow a black hole that fast. From a typical star-sized seed, there isn't enough time. But gravothermal collapse offers a dark solution. Imagine a massive dark matter halo forming very early in the universe. If the interaction strength is high enough, the core of this halo collapses before the galaxy even finishes forming around it. It doesn't make a small, 10 solar mass black hole. It collapses directly into a monster of 10,000 or even a million solar masses. This heavy seed gives the universe the head start it needs to build the giants we see with the James Webb Space Telescope. Recent studies from 2024 through 2026 have linked the abundance of these high redshift quasars directly to the properties of dark matter. By tuning the interaction strength in our models, we can match the number of monsters we see in the deep universe. The heat death of the dark matter core is the birth of the galaxy's central monster. This theory also explains the diversity problem. Why do some galaxies today have flat cores, while others have dense, cuspy centers? In the cold dark matter model, this variety is a failure, but in the gravothermal model, it is a feature. We are looking at a population of galaxies at different stages of their lives. Some are young, in the core expansion phase. They look fluffy. Others are old and have entered the collapse phase. Their cores are shrinking and becoming dense again. The concentration of the halo determines how fast this clock ticks. High concentration halos collapse faster. Low concentration ones take their time. To make this work across all scales, from tiny dwarf galaxies to massive galaxy clusters, physicists have refined the model to include velocity dependence. This is similar to Rutherford scattering in particle physics. The idea is that the faster the particles move, the less they interact. In dwarf galaxies where speeds are low, interactions are frequent. Cores form and collapse efficiently. In galaxy clusters, where speeds are incredibly high, the particles zip past each other without interacting as much. This keeps clusters looking more like the old cold dark matter predictions, which matches what we observe. This velocity dependence is the key that fits the lock of observational data. So, do we have proof? We can't see dark matter directly, but the observational landscape of 2026 has given us smoking guns. First, there are the ultra-dense subhalos. Gravothermal collapse predicts that some clumps of dark matter should be denser than anything cold dark matter can produce. Gravitational lensing surveys have started finding these small, incredibly dense objects. They are likely the cinders of collapsed cores. Second is the black hole connection itself. If this theory is right, there should be a lower limit to the mass of a halo that can host a black hole. Below a certain mass, the core never gets hot enough to collapse. This predicts a cutoff in the black hole population in dwarf galaxies, something upcoming surveys with the Roman Space Telescope are poised to test. And finally, there is the possibility of dark radiation. If dark matter can cool down by emitting dark photons, the collapse would happen even faster. This would lead to the formation of dark disks and complex structures mirroring the visible universe. As we stand here today, the paradigm shift is palpable. We used to view the dark universe as a frozen background, a static stage upon which the drama of visible matter played out. Now we know that the stage itself is alive, it is evolving, it is flowing thermodynamically. The very interactions that puff up halos to solve the small-scale crisis are the same ones that eventually doomed them to a runaway collapse. It suggests that stability in the cosmos is temporary, given enough time. Every self-interacting dark matter halo will succumb to its own gravity. Its core will feverishly conduct heat outward until it implodes, leaving behind a black hole as a tombstone. The universe is not just holding together, it is burning toward a thermodynamic destiny that drives the formation of the largest structures we know. The dark sector is not a ghost, it is a machine. And it is running hot.